Hello, welcome to Yang Tutorial Part 1. In this module, we'll begin a detailed look at the Yang data modeling language with a tutorial on all of the basic statements of Yang. This will be continued in Yang Tutorial Part 2, where we'll get into some more advanced Yang statements. First, we'll take a look at the concept of Yang modules. We'll see that when you write Yang data models, you write some number of modules, or modules can also be decomposed into submodules. So let's take a look at the module concept. First here, we see an example of a Yang module header. We'll see that they start first with this module declaration, where module, and then there's a name of the module. When working with conf.d, your file name should equal your module name. So acme-module should be contained in acme-module.yang. Each module begins with a namespace declaration, which forms a unique identifier to distinguish this Yang model from other Yang models that may be in the system. Because when you're working with any netconf-based system, and also with conf.d, you will typically have some number of different Yang models that form the entire model set for the system. Each Yang module is uniquely identified in its own namespace. After the namespace declaration, we have the prefix statement. This is used as a shorthand notation to refer to this namespace if we need to later in this module. So in that case, we'd use acme : and then something, and that namespace is used to disambiguate references as needed. If you have worked with XML schema previously, the idea of namespaces and prefix are the same as in XML schema. Because remember, Yang is an XML schema definition language. It maps one-to-one to XML. After your module and namespace declarations, you'll have some number of imports and includes that are used to bring in definitions from other Yang modules, or to include submodules. There's an important difference between import and include that we'll talk about in a couple of slides. Your module header will also include identifying information such as the organization, contact, a description of the module, and then some number of revision statements to uniquely identify the revision of this module. Using the revisioning information in Yang gives you a powerful tool, because when working with something like netconf, in that hello exchange of netconf, the netconf server in the device will advertise all the Yang data models, i.e. the Yang modules which it has available, and the revision of those modules that are present, so that the management station knows exactly what a device has in it. Here is a basic sketch of what your typical contents of a Yang module will be. You'll have header information in the module. You'll have some number of import and include statements, followed by local type definitions, then any configuration or operational state data declarations, and then also any action or RPC definitions or notification definitions. For the import and include statements, there's a subtle but important difference to keep in mind about import and include. Import is used to refer to definitions in another Yang module. It pulls in references from that file. It does not pull in the body of the file that's being imported. So you may have type defs or groupings in another module which you wish to refer to. It's very common when you're doing Yang data modeling to write a module in which you have some common type definitions or groupings that you use across multiple Yang modules. The include statement is used to pull in submodules into a main module. A module does not have to be contained within one file. You can decompose it as necessary for ease of maintenance, design, etc. And the include statement totally pulls in that Yang file. So a Yang import is similar to including a header file in your C code. An include statement is similar to when you're writing C applications that are in multiple files. You compile them all each to object files and then finally link them into the final executable. In Yang, the include statement pulls the submodules into the module so that then you, at the end, have your fully formed namespace for that module. For submodules, we have an example here on this slide. On the left, we have part of the main module, Acme module, which we see does an include of Acme system. On the right, we see the submodule Acme system. So Acme module would be in the file acmemodule.yang. The submodule Acme system would be in the file acmesystem.yang. You'll see the submodule does not have a namespace declaration. Instead, it has a belongs to statement. That it uniquely identifies what module this submodule belongs to. A submodule belongs specifically to only one module because it's part of that namespace. Also, a submodule cannot reference definitions back in the main module, which is including it. You can only refer downwards, you can't refer upwards. So that's a basic introduction to the idea of modules. Now let's start talking about data types, and then later on we'll see how the types actually get used as we pull together a full module. Yang has a rich set of base types. All of these are defined in the Yang RFC number 6020. There are quite a few base types there. There's a sampling of them here on the right. There's various signed and unsigned integers, strings, booleans, enumerations, etc. A type that you use on an element that stores data, such as a Yang leaf or leaf list, will have a type that can either be a base type or a derived type. Derived types might be a simple type, or it might be a grouping. A simple type, such as a type def, is an individual data item. A grouping you can sort of think of as a structure. It's a grouping of multiple data items that can be pulled together. We'll show an example of a grouping later on during this module. For derived types, the Yang typedef statement is used. So it defines a new simple type. You take an existing type, either one of the Yang base types or a previously declared typedef, derive from it, and add some restrictions. This is very similar to how a simple type works in XML schema. So here we have an example where we're defining a typedef called %. It's based on the unsigned 16-bit integer base type, but it has added a restriction where it can take a range of 0 to 100. So when we have this leaf called completed, it has a type called %. So completed can take the values of 0 to 100 as a result. In conf.d, this sort of syntactic constraint of 0 to 100 is automatically enforced by conf.d when you enter your data. You don't have to write any syntactic validation code for your system when using conf.d because we automatically enforce that from the Yang definitions. So, a bit more on the types of restrictions you can use when using a Yang typedef. Here we show a couple examples using integers on the left. My base int32 type is based on a 32-bit signed integer, and then it can take on the values of 1 to 4 or 10 to 20. So that vertical bar is used for OR, just like in many programming languages from the C family. Below that, we see another typedef of derived int32, which is based on that MyBase int32 type we previously declared. Derived int32 can take on the range of 11 to max. So what this restriction does is take the restrictions of the base type and then apply the derived restrictions on top of it. So in this case, derived int 32 may take on the values from 11 to 20, since on the base type we're deriving from, its maximum value is 20. On the right, we see an example of strings. So we have my base string type, which can be a string, and that string is restricted to be the length of 1 to 255. You can enter any data into that string as long as there's 1 to 255 characters in it. Now, below that, we make typedef derived string that we derive from my base string type. Here, we're adding two restrictions. Now, the length restriction is 11 or 42 to max. So our string may contain 11 characters, or it may contain 42 to 255 characters. It may not contain 25 characters. That would be a violation. In addition, we've used the pattern attribute on this type so that it must meet this regular expression of this can only be an alphanumeric entry into the string. Again, these syntactic restrictions, since we can formally and precisely declare them in Yang, confd will enforce for us. Next, we have the union statement. Sometimes we have values that we want to have that may be a number or a string, depending on what the user enters and what we want to use in our program. That is where the Yang union statement comes into play. It allows the creation of these special types. It works much like the idea of a union in the C programming language. Here, we see that we've declared a type called threshold, and we use type union within threshold. So union can be an unsigned 16-bit integer which takes the values of 0 to 100, or it can be an enumeration with one enum value of disabled. So this means the user can enter the value of 0 to 100 or disabled. In, for example, the confd CLI, this will be rendered then where when they're setting the value of something which has type threshold, they can enter any number between 0 or 100 or the word disabled. Past the base types defined in the Yang RFC, there are also a number of common typedefs, especially for the world of networking, defined by the IETF in RFC 6021. So to pull in these common type definitions and use them in our module, that is where we use the import statement. So RFC 6021 is contained in a module called IETF Yang types. So we import it. Most commonly by convention, people use the prefix Yang when they're importing this standards-based module. There is no requirement for you to do so, but it is a common convention and can prevent confusion. So here also is the first time we've seen a use of the prefix. Earlier we had talked about defining a namespace and having a prefix, or when you do an import, declaring a prefix if you need to refer to something. So here we see if someone wants to use, for example, the counter 64 type def from IETF Yang types, they'll say type Yang : counter 64. On the right in this table, you see a list of some of the types defined in IETF Yang types, but you can see a number of things that are very commonly used when doing network devices. You have the idea of things like MAC addresses, IP addresses, prefixes, etc. So this is certainly a Yang module that you should take a look through. In fact, any of the IETF standard-based modules, such as 6021, there are a number of them out there now, are good Yang models to look through when you're getting started to see examples of real-world production use of Yang. The grouping statement. The grouping statement allows us to form a grouping of common types that we often use in our data model. For example, oftentimes you'll use an IP address and port number in combination instead of having to, during our Yang module, write leaf address, leaf port constantly all over our models. We can instead declare a grouping that we later reuse. In some way, this concept is similar to a structure definition in the C programming language. But here we see an example, a grouping called target that contains a leaf called address, a leaf called port. The grouping can contain any Yang structure. It doesn't just have to be a list of leaves. There could be containers, there could be a hierarchical structure in there, which then gets inserted at the point that it's actually used. Here we see that the types are IP address and port number that come in from some module we've imported previously and given the prefix of inet, and hence the use of inet : there. After that grouping definition, we see below it use of that actual grouping. We have a couple of Yang containers and then uses target. Container in Yang organizes our tree or our hierarchy. So we see sort of a pictorial representation of that on the right. We've got peer and destination in our tree, and then after destination, both address and port show up from having the grouping. When we look at the tree, there's no sign of the grouping once it's been used. There is simply the content of the grouping shows up at that location. You will commonly have groupings you use across all your Yang models. You'll commonly have type defs you use all across your Yang models. Those should be gathered together in a Yang module. Very oftentimes people will do a module that is company name -common.yang. For example, tailf -common.yang. You'll see a lot when you're working with confd. In there you can put type defs and groupings and then use them in other Yang modules. You can also refine a grouping statement when you use it. You may have a common grouping, but you want to tweak it a little bit when you actually use it in particular places. The Yang refine statement allows you to do this. So here we see on the left a grouping definition called target that provides leaf address and leaf port. And then on the right we see an example of a use of it. We've got a couple containers and then uses target, but within uses target we say refine port default 80. So what this does is take the leaf port and add the default 80 attribute to that leaf. So in this case, when under servers HTTP, the port number will have a default value of 80. So if someone hasn't entered a value, we've defined its default port value to be 80. So we finished looking at basic Yang types. Let's look more now at the Yang data definitions that will use these types, where we'll define and organize our actual hierarchy of data. So first we have the leaf statement. A leaf holds a single value of a particular type. We've seen a couple uses of leaf already as we were talking about types, but here we see the formal definition of leaf. There will be leaf. A leaf will have a name. It will have no children. If you think of your Yang hierarchy or tree as a graph, that graph has interior nodes and final terminal nodes in the tree. A leaf node is a terminal node in that tree. There is nothing below it. It simply has a type. It holds data. So a leaf must have a type attribute to declare its type. And then past that, there are a number of different attributes that may be applied to a leaf. Many of these attributes, if not present, have a default value as defined in the RFC. So here we see a couple of examples. We have a leaf called hostname that's of type string. It's declared mandatory true, so it must be present. It's config true, meaning it's configuration data. In fact, actually, the default value of config is true. So if config true was not there, it would actually be as if it was there as an attribute. And then, of course, a description. Secondly, we see a leaf called CPU temp. It has a type. It has a units attribute. It's declared config false, meaning it is not configuration data. It is operational state data. Here we see a list of the attributes that a leaf can have, and then definitions. Some of the main ones you'll work with are config, primarily config false to declare your operational data. Default, we'll give a default value for a leaf, so if someone doesn't enter the value, that default value will be used. Mandatory, when the user's entering this data or it's coming in from something like netconf, does that data have to be present or is it optional? Must, we'll see later on. It's a way of declaring integrity constraints or relationships between our data, type, etc. through the rest of these attributes. Again, you can get the full formal definition of all these attributes in the Yang RFC. Container is our first organizational Yang statement. It is used to organize our leafs into that hierarchy or tree. If you think of your Yang hierarchy as being, a graph of a tree, a container is an interior node of the tree. It is only used for organizing the tree. It doesn't have a type. It doesn't hold data. So here we see an example of container hierarchy of system contains services, which contains a container called SSH. Now here, this SSH container has an attribute called presence. A presence container is something special in Yang. A regular container is always there. That structure always exists. Presence gives you the ability to think of it as a dynamic or optional container. It may or may not be there. One technique you can use in data modeling is remember that things can sometimes have a meaning just by being present or not present. So there are some cases in your data modeling where instead of having something be a Boolean with true-false values, it may be more natural to use something like presence to say, if it is there or if it is not, and that has meaning. So here, although container SSH may or may not have something in it, most typically it probably does, but if you haven't populated it, that whole container doesn't have to be there in storage or in our hierarchy. Now, leaf isn't the only data containing statement in Yang. There are some others that actually have types and hold data. First is a leaf list. A leaf list has a type. It holds data, but it actually holds multiple data items. So in this case, our leaf list called domain search has a type of string. This domain search can contain any number of distinct strings in a list. A common mistake when people are first working with Yang is to think of a leaf list as an array. It really isn't. It's a list. It is a list of items. Now here in this domain search, we see the attribute ordered by user. Ordered by can also have the value of system. By default, leaf lists are ordered by system, meaning you can populate items in that list, and the system can decide what order to store them in or present them back to you. So you may enter them in one order, but later on when you show them, they may be shown to you in a different order than entry because the system is free to order them and store them however it thinks is most efficient. Ordered by user allows the user to control the order they are always presented if you do a show or if you access them from your applications. Ordered by user could be useful. So for example, this leaf list that's called domain search. This is a list of domain names that we want to search, and we also want to make sure that they are searched in a particular order. So maybe most specific to most general, closest server to furthest server. So here they've been declared ordered by user to control that order. Next is the list statement. The list statement you can think of as being analogous to a table definition. By the strictest definition, a list is not a table, it is a list that contains entries, but oftentimes when you're first learning Yang, if you think of a list as a table and the entries of the list as rows in that table, using that conceptual analogy makes it easier to understand and initially work with. So here we see a definition of a basic list. It's a user list, much like we'd have a user list, say, in a password file on a Unix system. A list will have a key statement to declare which of the list entries are the key values. There can be multiple keys, so these are essentially, think of as the key columns of your list. By convention, you should declare any of your key leafs first in your list entry right after the key statement. So after our key declaration, we see the leaf's name, UID, full name, class, which you can think of as the columns of our row declared here. And we see up top, kind of a pictorial representation of this list entry. Lists are similar to leaf lists. They could be ordered by system or ordered by user. Most commonly, unless you have a real need to control the order, just leave it at its default value of ordered by system. Since ordered by doesn't show up here in this definition, its default value of system is used. Now, lists and leaf lists have some attributes that you can declare for them in your data model. We've already talked about ordered by in previous slides. You can also have min elements and max elements to bound how many entries may be in the table. Perhaps you have a table that can contain 0 to 1024 entries. In that case, your min elements could just use its default value of 0, and you just say max elements 1024. This is an integrity constraint of our data, which will automatically be enforced by confd. Confd, if you have that limit of 1024 maximum elements, confd will enforce that for you and prevent the user from creating more entries from that. Lists have key entries. The key, as we mentioned earlier, there can be one or more keys. If there are multiple keys, it's the combination of the keys which must be unique. The key field is used to specify which list entry, i.e. row, we're referring to, and so as a result, keys must be uniqueness. And again, uniqueness of keys is automatically enforced by confd. Now, an important thing that we see in the lower right here are what is called key paths. In Yang, if you need to refer to specific data items, you'll use an XML XPath. When working with confd, we use a simplified variant of XPath, which we call key paths, to refer to items. A key path is simply a /separated list of names, which is the path within the tree. So much like when you're working with a file system and you have a directory path down to a file, you have in Yang a path to a data item. In the confd APIs, we will see that these key paths are used to specify items when we're interacting with confd from our application code. If you need to specify specific key values to get to specific rows, that is when this curly brace notation is used. So user and name come from our Yang hierarchy, where we had the list user and a leaf called name, but if we need to get, say, name, UID, from a specific row, we need to provide the key value or values for that row. So in this case, we see a populated sample table. So using the username Yang, if we want to say what is the UID of the user Yang, this key path / user curly Yang curly / UID is used to refer to it. If you had multiple keys in a Yang list, you would space separate the key values within the curly braces. You could have different keys based on your declaration as well, depending on what you want to have in your Yang file. We also do have in ConfD the concept of what we call secondary indexes, where you may have one key or set of keys declared in your Yang module, but you often want to traverse the Yang list in a ordered based on some other field, so you can use the secondary index concept in ConfD as well. Now, I previously had mentioned keys, we have uniqueness enforced on them. However, sometimes in your Yang lists or tables, you have some non-key entries or columns that you want to be unique. Perhaps you have a list of server names and you want the combination of IP address and port number for that server to be unique across all rows of that table. That is where the unique statement comes into play. You can form uniqueness groups, like in this slide, one field, so name, we've changed our key to be user ID, and then we have the name column, but we want all username, even though UID is our key, we want all usernames to be unique, so we add the unique attribute to the list to have that uniqueness group. There can be multiple uniqueness groups, and within a uniqueness group, the combination of items must be unique. Here we see some examples of multiple keys in a table. Here we have a simple route table, which is keyed by an IP address and a prefix value. So the combination of IP and prefix is what must be unique across our table. So here we see in our list declaration the key statement having both IP and prefix present, and then also an example of a key path where in the curly braces we have the values of the IP address and the prefix separated by a space within the curly brackets. Note that that key order is significant. The values of keys within the curly brackets of a key path must match the order that those keys appear in the Yang data model. Next, we have leafref. Leafref is used to model relationships or constraints among different parts of our data model. If you have worked with XML schema previously and are familiar with XML schema's concept of a key ref, a leaf ref in Yang works similarly. However, in XML schema, a key ref can only refer to a key field. A leaf ref is more generalized and can refer to any leaf in the model. So effectively what it means is when we get to that point of a leaf ref, the only values that can be selected are values from what is being pointed at by the leaf ref. So here we first have in our model somewhere an interface table is shown in the upper left, but then we also somewhere else in our model some RIP routing information. So we see the model for that RIP information is a list of network interface names that we're using RIP over, and any interface name we put into this list is of type leafref pointing to the path, and in this case the path, since we're in Yang, is actually an XPath of /interface/name. So what this means is when I'm populating that RIP network interface name table, when I select values for IF name, it is only valid for them to be existing values in the interface table, the interface name path that's pointed to from that path argument. So since here I have 3 interface names defined, when I populate IF name, those are my only valid choices. When you're working with ConfD and any of the auto-rendered human-machine interfaces, you'll see that the user is constrained to only entering those values. ConfD automatically enforces those leaf refs for you. Similarly, for things such as netconf, that enforcement is done as well. Now, also, in this case of, say, IF name is pointing to ETH 0.19, someone cannot go into the interface table and delete ETH 0.19 because there is a existing leaf ref that is pointing to it. That referential integrity is maintained. If someone tries to delete ETH 0.19 from the interface table, they'll get an error because it's being referred to. So this prevents creation of dangling references. They'd first have to remove the reference to ETH 0.19 from their RIP IF name, then they could remove it from the interface table. So again, all these sorts of integrity constraints, etc., are all examples of the automatic validation that ConfD does for you, just based on having defined it in the Yang data model. Now, there are cases where you may want to do a leaf ref to another list, but that list has multiple key values. And so you need to refer to both of them and keep that combination unique. So that is where proper use of XPath in your leaf ref definitions comes into play. So here in our example, we have a container called video that has a IP address and a port number that needs to be selected from the client table. So declaring the first key of VIP is simple. We do a type def or a type of leaf ref that has the path of client IP. Now, if you look at that populated example, you see client IP 12.36.219 appears twice with 2 different port numbers. So once we've pointed to an IP, we want to constrain the user so that they can only select ports that come from the selected IP. So then when we declare this leaf V port, its leaf ref type has an XPath of, you can see the main parts on the left and right of client and port, but within square brackets, which is used to select a node set within XPath, we see IP equals current, meaning the value of the current node / VIP. So this allows us to kind of go up the tree, back down. And what this XPath incantation does is say, take the value starting at the current node, which is pointing at vport, ... takes us up to video, and then finally the /VIP takes us to VIP. So in the video list, in this row entry, taking the IP value that is in this row entry and then using that to look up in the client table to get the ports that are valid for that IP. So by writing this XPath, we've gotten that extra integrity constraint so we can do a multiple key leaf ref. We'll see more about key paths in subsequent modules in this training video series. There is one thing, though, in ConfD that helps with XPath that is a tailf extension to XPath, which is the deref operator. So I just sat and explained how these key references work of, IP equals current, blah, 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 blah. If you start having, say, 3 keys like we show in this example on the left, by the time we get to that third key, the XPath gets a little bit more convoluted to declare So as syntactic sugar, we've introduced this deref operator that allows you to more easily refer to these paths. So, if you look on the yellow highlights here on the slide, you can see the standard XPath statement and then the simplified version using the deref operator, which makes it much easier to implement. Now, let's talk about the idea of actions and notifications to wrap up this module. In Yang, you can declare actions, also known as RPCs. In netconf is an extensible protocol. You can add new operations, i.e. RPCs, to the netconf protocol, which will then allow you to trigger something to happen specific in your device. And this can be done via the RPC declaration. This is the Yang declaration of a new netconf RPC. In conf-d, we will also render these as actions you can trigger from other interfaces or APIs. So here we show a simple RPC definition. RPCs have a name. This will be the actual RPC name used in the netconf protocol when the RPC request comes from the management station. And the RPC can have both input and output parameters declared for it. Here we have a simple parameter declaration. We have one input leaf called image, one output leaf called status. You can have any sort of Yang hierarchy within those input and output parameter declarations. They could be a container, it could be lists, whatever meets your actual needs. Now, when defining a new RPC, keep in mind that if you're using it over netconf, your device will accept that RPC, process it, provide the returns, but then your netconf client at your management station must also know about this RPC and be able to use it. By having it declared in the Yang module, this gives your manager the knowledge that that RPC exists, and if the management station's been implemented to actually then take that from the Yang and use it, you may do so. Also, Yang is used to declare any of our netconf notifications. Netconf notifications are a way of having the device be able to send event information to the management station. Much like in SNMP, we have traps. We'll talk about netconf notifications in a separate module of this training series, but to declare the notifications that your device might send, they are declared in your Yang data model. So here we see an example of a notification definition. There's a notification, a name, and then some sort of contents for the payload that will be sent with that notification. This payload can be any sort of Yang hierarchy or structure there. Here, we're sending a notification called config change. That notification contains two parameters. A leaf, that here is the operator name, and then a leaf list, which is a list of the changes they've made. So for example, in the XML that comes out, that change list would look like what appears here at the bottom of the slide. So that brings us to the end of Yang tutorial part 1. This has given you a introduction to the very basics of Yang, types, data definitions, RPCs, and notifications. In the follow-on module, Yang tutorial part 2, we'll take a look at some of the more advanced statements in the Yang data modeling language. Thank you.